Hi, I'm Oliver Gao. I'm the director of Cornell System Engineering Program. I have been privileged to conduct what I call these systems conversations with our invited speakers here to be with us. So today I'm very delighted to have Dr. Ali Ross to be with us. Ali actually he is a visiting assistant professor at Purdue University School of Aeronautics and Astronautics. His research interests are in systems engineering, which is the right match to what our program is doing, and he's looking into system of systems and also information fusion. So Ali actually he holds a bachelor and master of science in electrical engineering from Iowa State University, and then he moved on to get his PhD in aeronautics and astronautics from Purdue University. So Ali, welcome, to our conversation. So, I was looking at, and also thank you for sharing, your CV with us. I was really impressed about, the diversified experience, you have had. Of course, your undergrad degree was in electrical engineering, and then you move on to, aeronautics and astronautics at Purdue. So I think I'm very curious to learn more about, how, your experience, how your career evolved to today, where you are playing some leading role in kind of I think driving forward the research in system science.
Okay, sure.
Yes.
Well, first of all, I would say thank you for the invitation, and it's a pleasure to be here at Cornell campus. It's my first time here, and it's an absolutely beautiful town, beautiful campus. So thank you for hosting me.
The weather helped today. Sorry, the weather was not too good yesterday.
No, it's a beautiful day outside today.
Yes.
All right. So regarding a little bit for my background is I got my bachelor's and master's in electrical engineering. Right after my bachelor's in electrical engineering, I started working for Honeywell Aerospace, and that was my first introduction to systems engineering. Even though I had a bachelor's in electrical engineering, I was systems engineers working on communication, navigation, and identification systems on the aircraft. First introduction to systems, seeing how the life cycle develops overall. That you start with customer requirements, and then you take it through all the way to let's say functional design and system development, software development, all the way to verification and validation. And over the next 6 years, I worked in increasing roles of let's say responsibility within Honeywell's, moving towards flight control systems, commercial aviation, and developing more systems engineering techniques for these complex systems. One of the things that I sort of saw really lacking was mathematical foundations for doing systems analysis and doing complex systems analysis. As we were developing these systems, it's a more process-oriented approach. And that's where I started thinking about that there's so much we could leverage from mathematics and mathematical theories to facilitate systems engineering and systems design analysis all the way to verification and validation. So that sort of motivated me to take a step in a slightly different direction from an industry career progression standpoint. I said, I want to go back to school and get my PhD because I saw really an opportunity here to advance the state of the art in how would we do systems engineering with mathematical foundations for complex systems, and that's when I got introduced to the idea of system of systems when I got to Purdue.
I see. So that's wonderful, and you have this. Of course, we know that a lot of people after they get undergraduate, they move on straight to get their PhD. But in comparison, and you, I think I envy the experience you had. You went into the industry, and you had the hands-on experience that made you realize that in the practice, while a lot of real-world challenges, while people are trying to cope with those challenges, you felt that we were lacking of mathematical or theoretical kind of support. That kind of probably prompted you to go back, to do your PhD, and I think that's actually a very good experience. I unfortunately I didn't have much work experience, and I did this kind of straight through, and even until today, I'm feeling like I have a strong desire to be better connected to the real world, and I think of course you did the other way around. So Ali, I think it's kind of you had the working experience, and also you got a PhD, and also you work with multiple agencies on these complex issues. So what do you see? Of course, I guess every one of us, we have a aspiration to address some of the key societal challenges using our knowledge and using our effort. So if you think ahead about your career and what do you see as a key challenge or system challenges that you would like to devote, your career to? Like, what aspires you to, for example, wake up in the morning very excited and get into work? The system challenge. What do you see?
Yeah, I think that's a great question. And so to your first point earlier about going to industry and then coming back, I think that has been very it's eye-opening experience for me because now I'm able to connect what I saw in the industry, what are the challenges are, and as I'm teaching courses, I'm able to relate my systems engineering experience with the material that I'm teaching and provide real examples that I have been part of, that I've worked on, and I think that resonates really well with the students. They're immediately able to see the practical implications of the concepts, the theories that we're talking, and relating it to my personal experience on aircraft design or the systems engineering challenges, I think this adds to the classroom environment quite a bit.
That's very valuable to the students.
Yeah.
Yes.
And so to your second point there about what keeps me motivated, I think there's two aspects to it, two points that I want to elaborate further. The first one, I think as our world is getting more and more complex, we rely on integrated systems that soon would be making their own independent decisions. I think as we are increasing our knowledge of autonomy, as we are coming up with more and more smart systems, there's going to be a time when the smart systems are talking to other smart systems in order to provide support for the human societies and human interactions. So that's the challenge that I think we need to address from complex system standpoint. And how do we integrate these complex, independent, and smart systems together? Whether that's an autonomous vehicle transportation network, right? Whether that's a space exploration problem, there's going to be smart systems that are designed to operate on their own independently. And we're getting good at designing those systems. What we're not good at is integrating them. And the problem with that is, how do we cross then disciplines? How do we cross the disciplinary boundaries to bring these systems together? And that's like a research area that I want to focus on. How do we come up with more holistic design of integrated autonomous systems? That's my sort of research goal. I'd say that's something I could dedicate my career to. And as we are doing that, I think we need to train the next generation of thinkers, systems thinkers, on it's not only about individual systems, but it is how we integrate systems together and how the whole is formed by multiple interactions, multiple interdependencies that often are transdisciplinary problems. So how do we train our students to think more in systems and holistically? One of the examples that I give in my class and that I sort of got from Kabira's research labs on systems thinking is that when you open up your tap water, you see the water coming out in your sink, but that water is a planetary system. Right? It's linked to the entire planet, and you need to be able to think in that terms. Oftentimes we don't make those connections, and that's the connections that I want to teach students on towards complex systems.
I think that's a beautiful point. I think it's kind of while you yourself being motivated, inspired by this complexity of the system and the need to address these issues, and I think I appreciate you pointed out the point. You pointed out this very important issue of training our future generations. Yeah. So this probably kind of, I'll go with the flow. Probably a little bit off from my script. Okay. The question I had. So I know it's been regarding training students with system thinking capabilities. That kind of reminds me. I know it's hard, but what do you see as a good definition? Would you try to define like systems engineering? I know like kind of people have been many people, they have different views, but I think you mentioned quite a few keywords that different people use to define system engineering. The reason why I was asking you this question was because yes, I think a lot of us, we realize the need of training students with system thinking and capabilities. But then if we push a little bit further, what kind of specific tools or framework that we would like to equip the student with? That immediately drive us to how do we define systems engineering? So probably I think my two follow-up question would be, how would you define systems engineering, and based on your definition, what core skills or capabilities do you feel we need to kind of train the future students with?
That's a good question. And for defining systems engineering, I think I'm going to refer to, so in COSI, that's the International Council on Systems Engineering. They recently did an exercise where they got all the NCOSI fellows together. And then they asked them this question on what is systems engineering? How has it evolved over the past few years? And how would you define a systems engineering? That's sort of like I start one of my lectures with that definition, is that systems engineering is really a transdisciplinary endeavor where we are developing or we are developing an engineered system, right, that interacts with an environment, and we're looking at different disciplines, how they come together to provide the capabilities of that engineered system. And I think that's one of the key elements there is the transdisciplinary approach. That it's not only one discipline. Aircraft, for example, you can say that belongs to an aero department or mechanical and aerospace engineering. But in reality, aircraft teams are very diverse. Just even designing that from marketing, from customers' relations, how does the market analysis play into the aircraft design? How does the electrical engineers, the software engineers, the mechanical engineers, the air engineers, they all have to sort of work together. And systems engineering is about developing that framework that it remains focused not on discipline, but rather than on the engineered system. And I think, and that's what we got to train our students in, is that they pick a major and then they are educated in that field. But they also have to work with other engineers, other teams, and not only other engineers, I would say other disciplines. The business majors, the finance majors, right?
Yes.
And as for particularly for complex systems, I think it's becoming very important to even cross that boundary into the social sciences aspects and political sciences aspect too. Because as systems are getting more and more complex, we need our students to be able to interact confidently with these multiple disciplines, focused on how the engineered systems comes into existence. I think that's my definition of systems engineering, and that's what the goal that I want to pursue with my career is that how can we best train the students to achieve that goal.
I think Ali, that's beautiful. That's very important. I think this kind of helped me also because from the Cornell system and in a program point of view, we're trying to build a curriculum, right? We're trying to build a curriculum that will train the student exactly the way that you just described. Okay. I think what you just told us. I think can hopefully be very helpful for us, when we think about. But all those are the different elements. And you said that the people they need to work together. They need to work transdisciplinary.
Yeah.
But and then from a curriculum perspective, right? We need to think about how do we design courses. And of course, those courses they don't have to be traditional like lecture type.
Right.
There could be courses. It could be like a workshop.
Yeah.
Or it could be a studio type where students are working with even practitioners, industry partners work on those things. But again, the key purpose is to achieve what you just said. We do want to instill this kind of system thinking,
right.
This transdisciplinary capability into the students, such that, for example, after they graduate from here, either with a master's degree or a PhD degree, and they can go out in the real world to do what you just said. They will be confident.
Yeah.
They will be able to communicate and coordinate across different disciplines.
Right.
I think that's very important. Very
and
helpful.
That's, as you mentioned, I think a lot of in my courses I try to rely more on the project-based evaluation and assessment of students, provide them more opportunities to apply those concepts rather than testing them in a more exam-based setting.
Yeah.
And I think when it comes to systems thinking, there's often it is hard to come up with one answer or one right answers. There are multiple right answers to the problem. It depends upon your perspective and how you have approached the problem. And to be able to see that and share those right perspectives, I think that's an important aspect of education. Rather than coming up with one multiple choice question which is right or wrong, I think that's we have to sort of move past that.
Yes.
Yeah.
So I think it's kind of now, with this kind of general discussion of system engineering, and I think when you mentioned earlier, for example, you mentioned like smart systems, as example, talking about their interdependency, or even how do we integrate, different components together so that, that go from a smart component to the smart systems. And in these things, I think one of your key research area is actually on information fusion systems. I think this seems to me, quite a new word or new phrase.
Okay.
Can you explain to us, what do you mean by information fusion systems?
Okay, that's. I think I can certainly
yes.
do that. And that's a phrase that I've been promoting more and more, and especially in various different communities. The way I see the role of information fusion as a key enabler of smart systems and integrating that systems. And the reason I say that is the discipline for information fusion is about how we generate data, how we generate information, how we process it, how we associate it, how we correlate it, and then how we combine the information to develop better assessment of the situation, and then to use it for decision-making purposes. Now, when you look at in systems today, the sensor data fusion, or which the term that I usually avoid to use, I like to use information fusion, is very partitioned. Just developing a sensor, you can get a PhD just looking at sensor issues and how to collect data. Yes. And how does a sensor view certain phenomenology, right? You can get multiple. You can get like PhDs in just on the tracking side, on how do you develop, on to process the sensor data, and how do you track multiple objects. There have been books and books written on that topic. However, when you start looking at an information fusion system, the idea is that what is the cycle that goes from data generation, processing, correlation, fusion, situation assessment, decision making. Because the decisions that you're going to make is going to impact the downstream of data that you just developed your action based on, right?
That's true. Yes.
So in order to really assess this, we have to take a look at a system level implementation of this information fusion, let's say, chain. Which hasn't been really looked at a lot in the literature. So the idea with information fusion system is that we need to be able to evaluate this information fusion, the process of collecting, generating data, all the way to the decision making as a whole, because there are interdependencies between these processes. Now, these processes, on their own regard, are very complex.
That's true. Yes.
No doubt about that. And I think that's one of the reasons that we have stayed away from looking at it as a whole. Is because these individual pieces are also very interesting and very complex. So that, I think, so it's somewhat a safer approach, right? To understand these elements and not understand the whole together. And then my research has been that we need to do more. We need to bring systems engineering and systems thinking into the design of these information systems. And the reason I say that is because now these independent elements, they become part of distributed systems. If we are talking, let's say, a military example of integrated air and missile defense, we're going to have sensors that are generating information in space on the ground, right? And then we have to sort of fuse those decisions together and then make an action or take an action, right? And then there are all these interdependencies between these, between how you generate data, how you fuse data, and then the actions that you're going to take, and how it will impact the next collection of the data and the fusion of data. So that's what I've sort of worked on as part of my information fusion research. Now, going forward in future systems, when you look at the role of information fusion, with smart systems, they are collecting data, they are making decisions, and then they are sharing either the data or the decisions with the other systems as well, right? So I see information fusion as really the source of engineering collaboration between these independent systems. And that further sort of emphasizes my point that we need a more systemic view of the role that information fusion plays in complex systems and autonomous smart systems.
I think that's a very important perspective, and I think you describe, actually, with your description, actually, you also brought up naturally, the need of taking a system of systems approach to the information fusion systems. So when you were talking about this thing, I was just thinking to myself, of course, today's societal development and especially with technology and also with technology interacting with human beings. We are absolutely living in a much more complex world than our ancestors lived before, right? It's kind of, so when we go from a component level to a system level, things become one, more complex. Two, I don't know whether it's more or less resilient, right? Because when we have two more things, right? One failure of one thing could lead to the failure of the whole system,
Right.
right? And also another thing is really, like people, I don't know how you feel, when you go from a simple thing to a more complex thing. Some people, they will get excited, but some people will get scared, right? Wow, this is really, so complex, and I don't know even, our human beings are going to be able to, get our arms around it.
Yeah.
So so when you go, since when you are, looking into these areas, especially in information fusion system for future smart systems, that's definitely more complicated.
Yes.
And of course, with all this data, and of course with this data, and essentially each one of us will probably become sensors ourselves, right? And the data will be collected, and the decisions will be even made thousands of miles away from what our behavior is. So what's your overall feeling? Are you excited or are you scared, and why?
That's a tricky question.
By the way, this is
I
not
think-
on my script,
Yeah.
just
I think I am, as you mentioned, I think I would say I'm both excited, and I think my my role as a researcher and as an academic is to contain that the scare factor a little bit, right? So dedicate my research and approaches to better assess these systems so that we can develop confidence and we can develop trust in distributed systems. I think one of the main issues there is that we are unable to comprehend the complexity right now for these distributed and complex systems. We are very good at looking at one particular discipline, going down into the details and understanding how that works. Is it when things starts collaborating and communicating with one another, and then the functionality emerges, right? That's where we become a little bit uneasy about it. So it is characterizing of that emergent behavior, which I think it's a classical problem in complex systems. I think we need to be better able to predict, account, and then verify and validate that emergent behavior, understand the emergent behavior. And that
systems thinking.
Exactly, right?
Yes.
Systems thinking. So I think that are the tools that are needed to engineer the future, right? And be confident about it, not be scared by it.
I really like your answer. Actually, I was thinking.
That was also on the fly, so.
Yeah, no, that's great. I think I was thinking because I really like the word, like you kind of through, as a researcher, by working hard and doing research into this area, such that we can help contain.
Yeah.
Right.
So
the,
that's
the
exactly
scaring factor, and then getting us, excited and confident.
Yeah.
And I think that's really, that's the only right attitude towards that, because we think about this, no matter you are scared or not, it's happening.
It is happening.
It is happening. So as a result, you have to. So in that case, since something you have to do it, it's better to do it, right, in a positive way instead of being scared.
Yeah.
Right? So I think that it's really, I think, a good attitude. So speaking of that, now I want to come back a little bit. Kind of, you mentioned a little bit about the application of information fusion systems. Can you give us some more examples of applications of information fusion systems, such that I think people can get better understanding and also get better appreciation of why information fusion system is going to be very important to our future world, especially the smart systems.
Okay. Sure. So on the application side, I've worked quite a bit on the integrated air and missile defense side, right? Coming from the DoD side of things, and what I've looked at is once we are designing the large-scale complex systems, information fusion is playing a key role in it, and that role has to be carefully engineered at the system level. just by adding a new sensor, does the overall system performance increases or decreases? If I add a new sensor which provides 10% better capability than my old sensor, for example, does my overall system performance increase by 10%, or does it increase only by 5%? And if it does increase by 5%, why? I think that's the question that I have looked at with my research, and I have developed these machine learning tools and statistical approaches for information fusion systems that help investigate why that is the case. And if I add a new sensor, for example, if I make one change in my information fusion system at one side of my system, how does that change replicate throughout the system? And what other changes do I need to make in order to maximize the benefit from that new addition? So that's the application area that I've worked on personally over the past few years. Yeah.
Mm-hmm. I think that helps a lot, kind of, for people to, again, appreciate some kind of specific needs of these, I think, information fusion systems. So Ali, I know, I'm very proud that you are also, in addition, being very active in your own research, you have been playing a very significant role in multiple organizations, and I know that you've been playing a key role in the complex system working group within COSI. I think, do you want to talk a little bit more about the frontiers that your working group is working on within COSI?
Sure. Yeah. So I would say in COSI, I've been quite engaged with COSI for quite some time now. That's the International Council on Systems Engineers, and I'm the co-chair for their Complex Systems Working Group. And our primary purpose for this Complex Systems Working Group is how do we promote better understanding of complex systems? How do we view complexity? What is really the definition of complexity? What adds complexity to a system? And then what are the mathematical approaches that could be used in complex systems analysis, design, evaluation, and leading all the way to verification and validation of complex systems. And in doing so, we also partner with a lot of other organizations and other groups within COSI, for example, System Sciences Group, and as they're developing system sciences, how those system science methodologies could be used in complex systems. The social sciences working group, it's actually a brand new group at COSI, and we're going to be collaborating with them to see how social sciences can be brought into the aspects from social sciences could be brought in to solve the complex systems problems. Yeah. So
I think that's a nice. It's kind of speaking that, like I probably mentioned to you before, like when our program started, our degree program in PhD, actually we called it PhD in systems. And we dropped the word engineering, such that it opens the door, for people with background in non-engineering disciplines. And I think we found out, that to be a very wise decision.
Yeah, and I think that's the way to get towards a truly a transdisciplinary program where you're able to bring these multiple disciplines together. I think that's what's needed for systems engineering and systems development for future. Yes,
that's right. So I noticed that you're also you're also directing these early career professionals, like for within the COSI. I guess that probably from that channel you probably interact with academics. You're probably playing a bridge between academics and not only in COSI but also the industry in terms of these kind of systems professional development. So do you have any observations or any insights that you like to share with people? It's the reason why I'm asking this, because from our program we're educating, we're training, like each year we have about say around 100 like master of engineering students who will start a career in system engineering, and also now we are educating PhD in systems. So like any insights in terms of career development for young professionals in system engineering?
So that's actually that's a role that I've been quite excited about, and I've spoken quite passionately about engaging the younger generation early on in systems engineering as our students are getting master's degrees and as their students are getting PhD degrees. What are the roles that in COSI can play in order to further their career, promote their career? How do we design the products? And how do we design the programs that keeps our younger generation interested in systems engineering and facilitate their participation in NCOSE and in these organizations. I think one of the key challenges that's been faced by, and I've seen that across the board, I've been involved with AIAA Young Professionals and IEEE Young Professionals a little bit, and I think the challenges are quite similar between the two, that the way these organizations have evolved and the products that they have created, particularly in NCOSE, it caters to more experienced professionals. And but in order to continue moving our discipline forward, we need to get the younger generation involved early on in this too, so that they can take on the batons and lead the way forward. So how does the NCOSE needs to reform now, and what programs and educational activities that NCOSE needs to create in order to create better systems engineers and deliver the value to younger professionals?
That's beautiful. That's beautiful. And speaking of that, now I want to kind of dive a little bit further into some kind of the depths of your research, so that you can really showcase things that you're good about. I remember back in 2018, and one of your papers, you got this outstanding contribution best journal paper in this system engineering journal. So the paper's title was Systems Architecting and Design Space Calculation. So can you talk a little bit more about that paper, and what issues you look into, and what were your major contributions and also findings?
Sure. So this paper, sort of like a little bit of a risky paper. It talks about a process for developing a system, and it starts at a very operational, at a very high level. Start with an operational concept. So this paper goes into the detail. If you start with a very high-level operational concept, how do you then use model-based systems engineering to decompose into a functional architecture and a physical architecture, and then combine those two architectures into form of an allocated architecture to achieve that operational concept. So I think this framework is quite well established and understood in NCOSE. And systems engineering and system design communities. But the major contribution for this paper was take that model-based systems engineering representation and pair it with agent-based modeling structures, and say that these functional architectures and physical architectures, they have their own dynamics on how those functions are evolved, what are the physical constraints and considerations. Especially when we're talking about distributed systems and system of systems, they're widely distributed, space, air, ground, sea. How does those implications impact the allocated architecture and allocated architecture performance? And then pair these variations with statistical approaches and machine learning techniques to really understand if I vary something in my system architecture, my functional architecture, my physical architecture, my allocated architecture, that impacts the dynamics on how those functions or physical attributes are achieved, and then consequently it impacts how well you're able to achieve those operational concept. So then starting at a very high level and bringing it all the way down to the functional and the physical decisions, and how those decisions interact with one another in order to shape the performance of the system. I think that was one of the main contributions for that paper.
And that sounds great.
Yeah. And then I was very humbly informed that paper was selected for as an outstanding contribution for 2018 as the best paper for Systems Engineering Journal.
Yeah, I think that it's really, I think, as you mentioned, how can we translate these high level, different aspects of the stakeholder needs, and all the way down to the functional level and even component level, and the decision variables, right? How do we translate those things? And this is really, it's architecting. Right?
Yes.
It's really architecting, right?
So one of the key elements there, and I think the ones that I have been concerned with in industry, what I've seen, is system architecture is often divorced from design. You come up with the architecture, and that's some other team, another department, system architectures is defined, and then that architecture is given to the design teams, and they go and design it. And then they optimize their own individual pieces. But this work, what I was aiming to connect the two together, at least at a conceptual level. What are the key decisions that the architect needs to know from the design teams, and what are the key decisions that the design teams need to know from the architect in order to come up or minimize the overall system performance. That was one of the thoughts behind this paper. Yeah.
That's great. That's great. So with your interaction, with NCOSE and you yourself, like been practicing system engineering in your work, while we're excited about the power of system engineering that offers us, but in the meantime, I know like for any discipline, we face challenges and difficulties.
Mm-hmm.
So, what do you see as the major difficulties that system engineering? I don't know whether system engineering has established itself as an individual discipline, or kind of people were still working hard
Mm-hmm.
towards that. So what do you see as a major challenge or difficulties that, for example, to be more specific, like in COSI, could be facing?
Mm-hmm.
And
So-
what would be your recommended approaches for us to cope with those kind of challenges?
So one of the challenges I see within COSI is a lack of mathematical foundations for systems engineering.
Mm-hmm.
I think that's one of my key goals as a researcher, and I think that was one of my primary reason to start doing systems engineering research is how do we develop the core mathematical foundations
Mm-hmm.
for systems engineering. If we look at other disciplines, electrical engineering, mechanical engineers, they have a long-standing history of how those disciplines are involved, and there are core theories about it.
That's right.
So if in electrical engineering, we can always talk about Kirchhoff laws and other
control
key
theory.
the control theory,
Yeah.
right? There's no theory for systems engineering, and I think that's one of the challenges, the community, that we need to build and develop that theory and the mathematical foundations for this theory and how that is then applied for engineering systems. I think that's one of the key challenges. And in order to do that, it's not only just making systems engineering a discipline of its own, and I fear that's going to make us siloed in our own regard, right, in our own
Yes.
self. I think key element of doing that is discovering the systems problems that other disciplines are facing, and bring it and solve those in conjunction with the systems approaches, and that will help sort of bring those theories together and build a common theory that could then be applied across disciplines. I think that's one of the key challenges for systems engineering, and we need to as we make our systems more and more complex, as we are getting more and more reliant on independent decision-making systems, we need to address this as a community very soon.
Mm-hmm. I think that's you hit the right point. I think it's kind of you said about the lacking of like mathematical foundation, for the discipline. So do you feel? I think earlier you mentioned kind of, all these complex systems, unlike the previous individual component, you are integrating these things together, and there is going to be emerging features. So do you feel that, this kind of lacking of mathematical foundation challenge, if this challenge lies in bridging mathematical theory or mathematical foundation to system applications, or do you feel actually that challenge really lies in mathematics itself? So I'm just kind of imagine, does mathematics already have relevant tools or theories that can help us address these emerging features due to interdependent interaction, or you feel actually mathematics itself we're lacking? Yeah,
That's an excellent question, and I think we need to start at the first one first, where I believe there's a lot of good work that has been done in mathematics, and we haven't really discovered its proper application in system side yet. So that's one challenge, right? And I think that needs to be addressed very soon. There are excellent work in network theory or in graph theory, right? And applying that for systems analysis or complex systems analysis. What we don't have is well-established foundational frameworks that will connect the theory all the way to the application side. That's where a lot of system works comes into play now, I think. And then as we develop and as we apply more and more of these mathematical theories, as the systems problems get more and more complex, then we're going to start getting into the second aspect on do we have enough mathematical theories developed to be applied towards systems. I think that's one, I would say, leave for the future work right now.
Yeah, I think from what you were talking, kind of that one phrase came into my mind, because earlier we talked about system thinking. System thinking is one of the key kind of approach that distinguish like system engineering from other applications or other disciplines. But as you mentioned, and also for a lot of general public, when we talk about a system thinking, that our impression would be, oh, this tends to be on the soft side. And when you talk about system thinking, right, you are thinking out of the box, like you let your thinking goes anywhere, and then kind of, but that way, people will feel, oh, it's lacking mathematics.
Right.
Think about you're lacking mathematics. But how about, for example, if we, like I don't know, like in COSI, if we challenge ourselves talking about mathematical system thinking. So that could be kind of, make it, if someone even kind of, if they are able to kind of, by pushing towards mathematical system thinking or systems mathematics.
Systems mathematics. I think that's a core field that we need to develop, and
that's right.
And bring it towards develop that foundation for systems and systems engineering, how to apply mathematics to these problems. And I think there's a lot of opportunities there.
Yes. And, So I think we're getting to the end of our conversation, but I think with all your this kind of deep thinking and also your successful career so far, looking into all these different, not only system engineering application but also system engineering research. And what would you say to our PhD students in systems here? Like what insights or what kind of recommendations you would like to make to them so that they can make better use of their time here at Cornell?
Sure, I can. I think that's sort of put me in a little bit of a nostalgic situation here. Thinking back, going through my PhD graduate student years, I think that was a remarkable time. It was hard. It's difficult. It's challenging problems. But in hindsight, that's a very intellectually rewarding experience that I've had at Purdue University, and I'm very grateful for it. So for PhD students, I would say cherish your time here. That is that's really great time in their lifetimes to learn. And to grow and to get more and more education. And for systems PhD students, the one message I would say is don't get siloed in your disciplines. PhD can sometimes become very narrow focused, that you have to sort of go down into the details and you think that you're the only one working on that problem. But by collaborating and by exchanging ideas is where the magic happens for the PhD. So.
Beautiful, don't get yourself siloed. I think that's really a very key recommendation for students. That was great, Ali. It was great talking to you.
Great to talk to you too, Oliver. Thank you for having me here. I think it was a pleasure.